Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to be covering probably the most difficult concept pre-midterm, and that is a wrench. So, as you guys know, we've been doing force reduction, and we've been doing a couple things with force reduction. The first is converting all of those forces into a single force and a single moment. And then we took that one step further and said, okay, well, if we move that force, we can actually create that moment. So we were able to go from a force and a moment to just a force. Well, now we're going to get into probably the hardest, and that is when they ask you to create a wrench. And no, it's not the wrench like the tool, and that's what I thought it was, so it took me a while to understand what they were asking. But what a wrench basically is when the force and the moment vectors act in the exact same direction. So you're thinking, okay, well, that sounds really complex. And it actually can be, because to determine this wrench, we're going to need everything that we've learned so far, ranging from force vector addition, which you guys already know, moments, but then of course dot product. And I know dot product is one of the things students struggle with the most, and that's why this is a really good example, because it can show you how to use it to obtain the wrench. But again, a wrench is really hard to kind of describe, so I think it's best if we just get into it. So let's begin. Alrighty, so looking at this example, it says it wants us to replace the three forces acting on the plate by a wrench. Okay, well, we saw that coming. We already discussed we're going to do a wrench. But it also says specify the magnitude of the forces and the couple moment for the wrench and the point PXY where the wrench intersects the plate. So that's kind of a hint that, kind of like the last example, is we're going to have to move our resultant force a little bit to create a desired moment. But we'll get into that in just a little bit. The first parts of these force reduction systems are always the same, and that's in the sense that we're going to want to find the resultant force as well as the resultant moment due to all those forces. And if we look at this diagram here, well, we can actually do all that really quickly. So let's just start off and just kind of get what we know, and that's the resultant force, the resultant moment. So let's start off with the resultant force, and we know that there are three forces on this system. And what's really, really nice is each of those forces is in a different direction. So we can tell that the resultant force, Fr, in Cartesian vector notation, so it's going to be the squiggle brackets, will be something I. So if we look in here and look in the x direction, there's only one force that goes in that x direction, and that is Fa, right here. It's the only one that has a component in the x direction. So we know that the resultant force is going to be 400I. Alright, so now we look at the y direction, and similar to the x direction, there's only one force going in that y direction, and in this case it's Fc. So if we look at Fc, we see that it's 200, so we can go plus 200, and that will be in the j direction. And finally we have the k direction, or the z direction, and again, like the other two, which is very, very nice, only one force, and that is Fb. So we know that the resultant force in the z direction is going to be minus 300k. So very, very, very simple, but usually when that happens and they give it to you, oh, that didn't work out too well. If they give it to you and it's that simple to find, usually the rest of the question is pretty terrible. And as you guys will see, that's exactly what we have in this case. So we found the resultant force, so that's not too bad. Now we can move on and find the resultant moment. And what we can do is very simply, because these forces act in a certain direction, we can easily find them. So if I was looking at the moment about the x-axis for all these forces, well, let's just highlight the x-axis. Alright, what would make that rotate? And if we look here, nothing. Because there's a couple criteria that creates a moment. One is if a force, and I'll go to red here so we can kind of cross them off, is if a force, remember, to create a moment in that axis, the force has to be perpendicular in that plane. So if we look at Fa really quick, we know that that won't create a moment. So we're going to get rid of Fa. If we look at Fb, well, that is perpendicular in the plane, so that would create a moment. However, that force intercepts the x-axis, so that distance, that moment arm, will be 0. So Fb also does not create a moment. And similarly, FC, we know it's not in the right plane. That one's also not going to create a moment. If that distance is 0, it intercepts the axis. So if we look at this, we crossed out all three of our forces. So our moment in the x is going to be 0. And of course, it has units of newtons per meters, but it'll still be 0. However, the other two will have moments. So let's look at my. So now we're looking at the y-axis. Got to try and figure out, all right, what will create moments about the y-axis? So first thing, what intercepts the y-axis? Because remember, if it touches that y-axis, it's not going to create a moment. So FA, well, that actually touches the y-axis. So let's get rid of FA again. We look at FC. Well, that's actually right along the y-axis, so we can cross that off. However, if we look at FB, it does create a moment about that y-axis, the 300, and that's at a distance of 3 meters. So we know that this moment will be 300 newtons times a distance of 3 meters. So this will be 900 newtons times meters. So we do have a moment about y. 900 newton meters. And if we look at how that force acts, we can kind of see, and I'll go to red, that it's going to kind of rotate like this, which is counterclockwise about that axis, which means it's a positive force. So remember, you also have to try and find out if it's going to be a positive or a negative moment. So I'll just erase all the stuff around here. So we got our force our moment about the y-axis. And we can finish it up with our moment about the z-axis. So really quick, let's take a quick peek. Remember, rule number 1, if it touches that axis, it's not creating a moment. So if we look at this, FC, we know that that's not going to create a moment whatsoever. Rule number 2, which is it has to be in a plane that's kind of perpendicular. If we look at FB, plane that's perpendicular, the better way to describe it is if it's parallel with the axis. That's the best way to describe it. If it's parallel with the axis, it won't create a moment. So if we look at FB, it's actually parallel with the z-axis. So we know FB will also not create a moment. So that leaves us with FA, which is 400. So if we go down here, we can write down 400. And then we just have to find that moment arm. And that's going to be the distance from the force to the axis, that perpendicular distance. So we can see that that is 5 meters. So what we can do is we go 400, and we throw in a 5 there. And we know this is going to be equal to 2,000 newtons times meters. But again, we're not done there. We have to tell ourselves, okay, well, is it going to create a positive or a negative moment? So the best way to check right here is we're just going to go back to red, and we're going to see, okay, well, we can kind of see that that force will create something like this around the z-axis. And if we look at that, we go, okay, well, that's actually clockwise around that axis. So that moment must actually be a negative moment. So this will be minus 2,000 newtons times meters. So I'm going to erase this real quick. All right. So we found our mx, my, and mz. So we actually already have our resultant moment, mr, and then we can just put in 0i, because there's nothing in the x direction, and then plus 900j. So this is for my. And then minus 2000 k. And we can end those squiggle brackets, and of course this will be newtons times meters. So far, if this was a shorter question, we'd actually pretty much be done right here already, which is really, really nice. So let's just kind of summarize where we're at right now, what we have. So if I were to draw the origin, or I guess this would be point C. I'm going to draw point C because remember we took everything kind of there. So if I were to draw my x and y axis, so I'm going to go with something like this. X, y, and z axis, sorry. Alright, that's probably good enough, and I can just put the labels in. Oh, it's isometric. Hold on. Sorry, guys. Oh, when they do this to me, it always gets me. Alright, so this will be the z axis. I'm going to say that that is the x-axis. I'm going to say that that's the y-axis. Why not? I guess the opposite. So this is y, x, and z. So far right now we have kind of two forces in the end. We have our resultant force, which kind of goes from here kind of downwards. Again, this is not really to scale. I'm just trying to show you what our situation is right now. So we got a resultant force, so let's put this as FR. And then of course we have a resultant moment, which, oh, I should do it I'll do it in a different color. Come on, let's go pink. And remember, these aren't to scale, these are just kind of to show you our situation. So resultant moment. So I'm going to do that in purple. Remember, moments will have kind of one of those around it to show it's a rotation. I'm just going to go M, R. So this is what we have. We took all three of those forces that act at different locations along this plate, and we converted it into two forces, or I guess a force and a moment, that act at the same point on that plate. So now we say, okay, well, the question wants us to determine a wrench. It wants a wrench. So what it's asking for is it wants our force vector and our moment vector to act in the exact same direction. So what it wants is for us to take that moment vector and make it act along FR like this. So this is where it wants our new moment vector. It wants it to be exactly in the same direction as FR. So if we actually remember the dot product, we know that this is going to be MR parallel. So the parallel component, which is a projection. So if we were to drop this down, we can actually find the projection of the resultant moment into a component of it which acts in the FR direction. So we can actually do that real quick. And yes, there is something that we're kind of overlooking, but we're going to talk about that in a couple seconds. Let's just focus on MR parallel. So remember, and this goes for not even just moments, but in the previous parts of the course, because I got a lot of questions about this, it's when something asks for the projection or the component of a force along a specific axis, you should always be thinking dot product. And when I say dot product, I'm not saying the one with the angle in it. We're not worried about the angle of the vectors. For this kind of question where it's asking for just the magnitude of the projection, you can find that very easily by just dotting the two vectors. So if we want that component of MR, we know it's going to be MR parallel is going to be equal, and we're going to take that moment vector, and then what we have to do is we're going to have to dot it with the direction of that force vector. So not the force vector, we want to dot it with the direction of the force vector. So I'm going to put that as UF. So we don't know that UF really quick, but we can find it really easy because we know that to find a unit vector of a force vector, well, we can just take the force vector, which in this case will be our resultant force, and we can divide it all by the magnitude of that resultant force. So it's going to be like this. So if we put this into kind of our formula form, go up, we see that our force vector is 400, 200, and negative 300. So we're just going to go 400I plus 200J, and then minus 300K. And it's going to be divided by the magnitude, but since we know the vector, we can easily find that as 400 squared plus 200 squared plus 300 squared. So I can just throw this in real quick, and just like this. So this is how we find the unit vector. We do all the math and we divide all the components by the magnitude, and what we get is 0.743I plus 0.371 in the J direction minus 0.557, and that's in the K direction. Get in the brackets, and remember this is a unit vector, it's not going to have units. So now if I look up at this MR parallel right now, the magnitude of it, I have both components because I have MR and I have the unit vector. So if I were to go MR parallel, that's going to be equal to, and I'm just going to take all those things and start dotting them together. So for MR in the I direction, I got 0. And then for the unit vector, I get 0.743. So this is just going to be 0. Then I go plus, and I look at the J components. So for MR, I have 900. And then for the J component of the unit vector, I got 0.371. And then my last one, If I look up, I remember it's negative 2,000. So remember, you have to put the negatives into the dot product if you have them. And then for the unit vector, I got 0.557. And if I do all that math, I'm going to get right here that the component of it is going to be 1447.9 newtons times meters. So what does that mean real quick? So let's just draw out our scenario yet again, because this is really how the best way to understand it is just drawing it out. So remember, we have a force vector, and I'm just not going to draw the axis. I'm just going to try and kind of keep it in 2D to show you guys exactly what we're dealing with. So we have our force vector. I'm going to draw this a little bit shorter just for artistic reasons, as you guys will see. So this right here, this is our moment vector, our resultant moment vector. And I should probably label this. This was our force vector. And what we just did is we found the parallel component using the dot product. So what that means is if I were to project this down onto the force vector line, so this right here is 90 degrees. 90 degrees, so I just made a triangle, that this length here, this length, this magnitude right here, that's going to be the 1447.9, and that'll be Newton meters. So this right here, what I can also do, if I know the length and I know the direction, because I know that that MR parallel has to be in this direction. Oh, I should put the these kind of signs on to show that it's a moment vector and not a force vector. So I'm just going to draw one on this side real quick. So if this is the case, and I know the magnitude of MR parallel, so what I'm going to do is this right here is the magnitude of MR parallel. And I can easily find MR parallel like this, because I know, and this goes for all vectors too, that's not just this one, is I can find MR parallel, or any vector, if I just take the magnitude of it and then times that by the unit vector of its direction. So we know that MR parallel is going in the direction of the force vector, so this is going to be UF. So I'm just going to take that 1447.9 and I'm going to throw it into that unit vector at the very, very top. And what I get in the end is this is going to be equal to brackets 1075.9i plus 1537. Oops, sorry, not 15, just 537.2j, and then minus 806.5, and that one's in the k direction. And this will have units of newtons times meters because it's a moment. All right, so now if we look up at our diagram and you guys think, okay, well, maybe we're done. Maybe we're done. So we look, what we did is we had a force vector and a moment vector. They were going in different directions, but then we used the dot product to find the component of that in the same direction. So right now we have FR and we have MR parallel. So that's kind of what we wanted. The wrench, the moment vector, and the force vector, they're in the same direction. We should be good to go. But this is the only trick that you're going to need to kind of remember for wrenches. It's that when you take the component of something, think of 2D, XY plane. If this was our XY plane and we had a theta right here, well, basically we just took our resultant force MR and found the X component, or MR parallel. But remember, it's actually made up of two components. So yes, we found MR parallel, and that's great. However, there's actually another moment vector that goes like this, and this is MR perpendicular. So this right here, MR perpendicular. So in this current scenario right here, we can draw it out again. This is what we have at the origin. So I'm just going to put this as my point real quick. So right now, in this current time, we have a force vector. So I'm just going to put this as FR. We have a moment vector that runs perpendicular, which is MR parallel. So right here I'm going to put MR parallel. And I should probably put the vector hat on this one. So if this is what we want in the end, so we're very, very close. However, the only thing that we also have to consider now is we also have a perpendicular moment vector right here. And this is MR perpendicular. So we're getting closer because I have one of the moments in the same direction of the force. And remember, that's the end goal. Oh yeah, and this is perpendicular, so we can put perpendicular. So how do we get rid of MR perpendicular? Because that won't have any components in the same direction of the force. We can't go back to dot product anymore. But this is when you're going to have to remember kind of what we did before is if we have a moment vector and we want to kind of get rid of it, and in this case, we want to get rid of MR perpendicular, we can move the force vector in the plane. By moving it around in the plane, we can create that moment just by the distances. So that's what we're going to do is we're going to get rid of MR perpendicular by moving the force vector. So I'm just going to write that down. Moving the force vector. All right, well, to move the force vector, we know how to do it. We've already done it. And we got to think of, okay, well, we use the cross product, and that requires three things. It requires the position vector, but actually the position vector, that's what we want in the end. So we don't need to worry about the position vector. Actually, we'll write it down. So we know that a moment vector is equal to the position vector cross the force vector. So this position vector will have the x and the y that we need to solve this question. So that's what we're looking for, is that position vector. So if we look, we need the force vector. Okay, well, we actually know the force vector. That's our resultant force. So that's good. That's good. So the only thing that we need is the moment vector. And okay, well, that'll be the moment vector that we want to get rid of. So in this case, the moment vector is going to be MR perpendicular, and we don't know that yet. So this is where things are going to get a little bit more tricky. We don't know that perpendicular component. So now we have to go up here and look at this and kind of use what we know, and that's vector addition. So looking at this, we know that if MR is the resultant force, so MR, that's what we have in the end. And we know that it's comprised of those two components, MR parallel and MR perpendicular. So we know that this is equal to MR parallel plus MR perpendicular. And in this case, we know MR, we know MR parallel, so we can rearrange this formula to say that MR perpendicular is going to be equal to MR minus MR parallel. And we can solve that very, very easily. We're just going to take the I component of MR and minus the I component of MR parallel. And what you'll get in the end is MR perpendicular is going to be equal to, and then we're going to have our nice brackets, and it's going to be negative 1075.9i, and we'll look up and how we get these numbers after. So plus 362.8, so 362.8 in the j, and then minus 1193.5 in the k. And this will be newtons times meters. And in case you guys are kind of a little bit lost where I got these numbers, let's just look at the I component here. So we know that that's going to be the I component of MR. So if we go up and way to the top, we know that the I component of MR is 0. So this would be 0. And then minus the I component of MR parallel, which is the 1075.9. So minus 1075.9. And that's where we get that number from. So now we have MR perpendicular, which is exactly what we want. So now we can set up that cross product. So we know that our position vector that we want, it's going to be in the xy plane. Because we're going from the origin, which is 0, to some point in the xy plane. So we know that it's going to be x, y, and 0. Because it's in the xy plane, it doesn't have any z component. So the position vector is going to be xi plus yj plus 0k. And that units of meters. So if I'm doing my cross product right now, so if I find the moment perpendicular, we know it's going to be through the cross product. And put this down. We know it's going to be I, j, and k. And we know the next one's position vector, which is going to be x, y, and 0. So those are our unknowns. We don't know them. And we're going to finish it off with the force vector, which if we go all the way to the top here, is 400, 200, and negative 300. So we go here, we're going to go 400, 200, negative 300. So we're going to put this down, and then we can start solving this using the cross product. So let's just go through it real quick, and what we're going to get is something like this. So we're looking at the I components. We're going to have negative 300y minus 0, and that's in the I direction. And then I guess we should stick with the sign. So the next one, the j component, starts with the negative. And we go look there, it's going to be negative 300x minus 0. And that's in the j component. And we can finish it off with the k component, so plus, and this is the only one that gets a little bit longer. It's going to be 200x minus 400y. And this is in the k component. And we know that this has units in newtons per meters because it's a moment. So now we can take those components and start relating them to the perpendicular moment vector that we already got. So we know that for the I component, it's going to be negative 300y. But we already know that this has to be equal to negative 1075.9. 1075.9. And this is our equation 1. We can also look for equation 2 for the j components. What we get is 300x, and that has to be equal to the second component, which is 362.8. So 362.8, and dot dot dot. This is equation 2. And finally our last one, which is 200x minus 400y, is going to be equal to the final component, which is negative 1193.5. Negative 1193.5. That's equation 3. And what you guys will see, it's actually really nice because we don't need equation 3. We can solve for both x and y using equations 1 and 2. When you would need equation 3 is if it's not in the xy plane and there is actually a z component that you're going to have to solve. So for that, you'll need equation 3. For now, you're good to go. So from equation 1, we can easily solve, and what we get is from equation 1 is that y is equal to 3.59 meters. And from equation 2, what we can do is solve that, and we're going to get that x is going to be equal to 1.21 meters. And that right there is our final answer along with the stuff above. So right here, I'm just going to highlight that to show you guys what the numbers are. But the best way to answer this question and show markers exactly kind of what's going on is to draw a diagram. So what I'm going to do is I'm going to draw the XY plane. Oops, that didn't work out too well. Alright, so I'm going to draw kind of the 3 dimensions. And I think it's a little bit more flat than how I drew it last time. So let's try and make this a little bit neater. So what's going to happen is, remember, at the beginning we had all those forces. Just draw the axis. This is that y or is that x? That is y, perfect. Y, this one is x, this one is the z-axis. So we had all those forces acting at different spots. What we did is we converted those forces into a single force in a single moment, and we took that moment, split it into 2 components, a parallel component that ran along with the force vector and a perpendicular component that ran perpendicular to the force vector. And then what we did is we moved that force vector so that it would cancel out MR perpendicular. So and we found that point to be the 3.59 and the 1.21. So what we're going to do is we're going to put this point over here. So this is our point P, and at that point we have our force vector, which will run down something like this. So this right here is our force vector, resultant force, and we had a moment vector that ran in the same direction. So remember, that's what a wrench is when the moment vector and the force vector go in the exact same direction. So this is M, R, parallel. So that one's not the resultant moment, it's a component of the resultant moment. And of course this acts at a specific distance. So if I were to go dot, 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 and do the same thing this way, dot, 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 dot. What I'm going to put here is this one will be the 3.59 meters. And then this one is going to be the 1.21 meters. So our point, and then at that point we have a moment and a force vector. They run parallel to each other, and we have the values of those listed above. So this is what we get in the end. This is what a wrench is, and yes, it sucks. You guys probably already know that by now by doing this example. It's not fun. And this is why I call it kind of the kill shot of the midterm, because it's very difficult. And from what I've seen is very few professors actually do an example of it in their class. So when you get it, you guys have all the tools to solve it, but unless you know those tools very well, it's going to be very, very difficult. So that concludes this example. And with that, it kind of concludes force reduction. So the next example is we're going to do something. It's a little bit different. It's force reduction, yes, but it's different. But the thing that I like about the next one is it's realistic. So this right here, I don't know any scenario where you would want to know a wrench, if I'm being completely honest with you guys. But the next one is something that you guys will use heavily, especially after the midterm. Something you'll use all the time. So I hope you guys enjoyed the wrench. I know I do not enjoy the wrench, but hopefully you guys do. And with that being said, thank you guys all so much for listening, and I'll see you guys in the next video.